Hello friends, IBM is here with another episode of Learning Physics. It's a new year, it is 2023. Happy New Year friends. My message to you for this year is that share love with everyone that you meet, share love with the strangers. I know 2023 could be the year for you to finish your high school and you must be preparing um, for your end of high school exams this year. So it's 1st January 2023, and today I would like to take you to past paper questions. I would like to introduce waves. I would like to introduce a new chapter to you, and that is waves. Remember, this is AS Physics, and we are dealing with the solved past paper questions. This is AS Physics, and we are dealing with solved past paper questions. And to be specific, today we shall look at waves. Waves and Superposition has been made into one document. This is AS Physics past paper questions, and this is specifically paper 2. At this point, you must have downloaded the document for paper 2 and you must have printed it. It's hard to learn by just watching these videos unless you have a hard copy of these documents so that you follow through with these by writing actually on these hard copies. The documents are free. You can find them in the link or in the video description. The link attached to the video description. Download for paper 2, it is free. As soon as you use the link, the document opens for download. For paper 4, it will send me a notification to share the document with you. So do not forget to subscribe, share the document, download and print. You can print per topic. This is AS Physics, remember, Physics 9702. And this is going to be specifically part 2, paper 2. This is part 1 of waves and superposition, and we expect questions such as we shall expect to discuss questions about longitudinal and transverse waves, expect questions about electromagnetic waves, expect questions about superposition or interference, overlapping of waves, expect questions about stationary waves, expect questions about diffraction, gratings, and so many more. Therefore, do not forget to download the document and print. You can print that part of waves because this is very important. I want to let you know that this is one of the most important units because many times it carries the most or the highest number of marks in paper 2. It also carries the highest number of marks in paper 1. There are actually more multiple choice questions in paper 1 for waves than any other topic. Therefore, waves is a very important topic. When you are planning to, preparing for exams, you don't need to revise normally paper 1. You just prepare as if you are preparing for paper 2 because the questions will require the same concepts, only that in paper 1 they will be actually multiple choice but requiring the same concepts. So you prepare as if you are preparing for paper 2. That's how you'll also pass paper 1. Without wasting any time, I would like to take you to the past paper questions or the past paper document. At this time, I expect that you have downloaded this document. If you haven't downloaded, pause the video, go to the video description, copy the link, put it in your browser, then download the document for paper 2. It is called Master Key to A-Level Physics. That is Physics 9702. Revision questions paper 2. This is a trial edition that I wrote in 2022. That means in 2023 I will have to modify it a little. So those are mine. This is where I derive my name. I derive my name from this, so that one is not a big deal. My contacts are there in case you have a problem. You can always raise it to me. My contacts are there. My email address, my phone numbers. This is on WhatsApp. You can send me a message so that I can respond to you. Remember, this is a Cambridge curriculum. It may not be exactly matching with your the national curriculum of your country. So you must be doing Cambridge. But of course, physics is physics. Some of the topics overlap in all the curricula. So today we are going to look at waves. Waves, and this is page 453. So I'm checking for page 453. So here we are, page 453, and straight away I want us to start on waves. Question number 1. Remember, these questions are just cut or they are just sniped from past paper questions. And they are very important for your revision purposes. They will guide you, they will give you confidence in your practice as you prepare for exams. Number 1, sound waves are longitudinal waves. That is obvious. We all know that sound waves are longitudinal. By reference to the direction of propagation of energy, state what is meant by a longitudinal wave. In your class, you must have distinguished between a longitudinal wave and a transverse wave. And to be specific, we said for a longitudinal wave, the particles vibrate parallel. So for longitudinal, the particles vibrate parallel to the direction of propagation of energy. Yet for transverse, the particles vibrate perpendicular to the direction of propagation of energy. So for this particular question, we shall say that the vibration of particles the vibration of particles, or you can say the oscillation of particles. The vibration of particles, or let me say the vibrations of particles. The vibrations of particles are parallel to the direction of propagation of energy. The vibrations of particles are parallel to the direction of propagation of energy. That's what is specific with the longitudinal. Remember, for transverse, the vibration of particles are perpendicular to the direction of propagation of energy. Okay. A stationary wave. I want you to note it is a stationary wave. A stationary sound wave in air has amplitude A. In an experiment, a detector is used to determine A squared. The variation of A squared with the distance x along the wave is shown in the figure. So this is the variation. Remember, for a stationary wave where the amplitude is 0, we have what we call the node. And where the amplitude is maximum, we have what we call the antinode. So it means at this point here, the amplitude must have been 0, so we have a node here. This point here, the amplitude is maximum, we have an antinode. Here, the amplitude is 0, we have a node. We have a node, antinode. Here, the amplitude is again maximum, we have an antinode. So wherever we have amplitude is 0, just know that that is a node. And whenever we have amplitude maximum, just know that is an antinode. So state the phase difference between the vibrations of an air particle at x equals 25, x equals 25, 1, 2, 3, 4, 5, I think 25, no, 1, 2, 3, 4, 5, I think 25 is there. X equals 25, that is, we have an antinode there, and vibrations of an air particle at x equals to 50. You see, at x equals 50, it is also another antinode. So if you look at a stationary wave, I know you are used to these loops. you are used to these loops. Let me just draw for you the loops you are used to. You are used to such loops. Maybe I can draw it better. So you have an antnode here and another antnode here. Remember, this is a segment and this is another segment. So particles in two adjacent segments are 180 degrees out of phase. That's what your teacher must have told you. Particles between two nodes, if there's a node here, there's a node here, there's a node there, there's a node there, there's a node there. Particles between two adjacent nodes vibrate in phase. The phase difference between particles between this node and this node is 0. But the phase difference between particles between this antnode and the other antnode is 180 degrees because the two antnodes are in two adjacent segments. Therefore, the phase difference between a particle at x equals 25, that is in this segment here, and a particle at x equals 50, that is in the next adjacent segment, must be 180 degrees because this is a stationary wave. For a stationary wave, particles in two adjacent segments vibrate 180 degrees out of phase. Of course, 180 degrees is pi radians. Therefore, for this answer, for this question, it is easy to notice that the particle at 25 and the one at 50 are 180 degrees out of phase. I want you to note very carefully. For a stationary wave, where the amplitude is 0, we have a node. That's why I have put a node at every point where the graph touches the x-axis. Where the particle vibrates with the maximum amplitude, we have an antnode. That's why where we see the graph going to the maximum value, I have put there an antnode. At 25, 25 is in one antnode and 50 is in the next antnode. So there are two adjacent segments. Therefore, the particles are 180 degrees out of phase. The speed of sound in air is 330. Determine the frequency of the sound wave. So from the general wave equation, we know that V equals to lambda times F. They have given us the speed. All we need is lambda. Note very carefully that the distance between two adjacent antinodes is half wavelength. The first antinode is at 25, the next antinode is at 50. The distance between two adjacent antinodes is half wavelength. That is, distance between an antinode and the next antinode is a half, or is wavelength over 2. Therefore, we know that 25, so 25 is going to be wavelength over 2. 25 is wavelength over 2, which implies that, that symbol is for implying that wavelength is going to be 50 centimeters. The wavelength is 50 centimeters, or you can say it is 0.5 in meters. So we now have the freedom to find our frequency. So the frequency is going to be V, which is 330, divided by the wavelength, which is 0.5. And I will check my calculator. And from my calculator, it's like just multiplying 330 by 2, which is 660 hertz. Determine the ratio amplitude A of wave at x equals 20 centimeters over amplitude A of wave at x equals to 25 centimeters. So let's check the amplitude. Remember, this is a graph of a squared. So we shall have our ratio. We shall find the ratio. The ratio must be actually the square root of, because the graph is of a squared and we want only a. So it will be the square root of, let's see, a squared at x equals to 20. At x equals to 20, a squared from the graph 20. This is the value, which I think is 2.6 by looking at the scale on the vertical axis. The scale on the vertical axis is 1 divided by 5, which is 0.2. So 2.2, 2.4, 2.6. So remember, I'm finding the square root because we want a only, but the graph is for a squared. So this is the square root of 2.6 divided by, the other one is 25. I think 25 is 4.0. 25 is 4.0. So this is over 4.0. Remember to find the square root because the graph is of a squared, yet we want the ratio of only the amplitudes. So from my calculator, 0.6. My calculator gives me this ratio as 0.806, which is approximately 0.81. 0.81, two significant figures. So that is the ratio. Red light of wavelength 640 nanometers is incident normally on a diffraction grating having a line spacing of 1.7 times 10 power negative 6 meters. So that is line spacing. We normally, I think line spacing, that is D from a diffraction grating. You must have used the letter D for line spacing, I guess. Distance between two successive slits or lines. So D is 1.7 times 10 power negative 6 meters. Okay, they have given us the illustration here. Remember, theta is always measured from the central zero order maximum. The second order diffraction maximum, so n is equal to 2 because the second order of the light is at an angle theta to the direction of the incident light. Show that the angle theta is 49 degrees. So from the expression for diffraction grating, at this point, as a student who is going to sit for AS, you note that n lambda is equal to d sine theta. You must be having this at the tip of your fingertips. And they have given us the wavelength of red light as 640 nanometers, which is 640 times 10 power negative 9. So I'm going to substitute in this formula. N is 2, wavelength is 640 times 10 power negative 9 should be equal to D is the line spacing, which is 1.7 times 10 power negative 6, and this is times sine of theta. I don't always want to do a lot of mathematics here, but I'll simply divide both sides by this value here. This is wastage of mathematics, but I will show it. Sine theta is going to be 2 times 640 times 10 power negative 9 divided by 1.7 times 10 power negative 6. So 2 times 640 exponent negative 9 divided by 1.7 exponent negative 6. Sine inverse of the answer. So the sine inverse, it is giving me theta as 48.85, 48.85 degrees, which is approximately 49 degrees. Determine a different wavelength of visible. The word visible is made even clear. Determine a different wavelength of visible light that will produce a diffraction maximum at an angle of 49 degrees. So it means the angle has not changed. The angle has not changed, but the wavelength is going to be different. Remember here we had used the n was to, let's check n equals to 3 and substitute in the same formula. For n equals to 3, for n equals to 3, we are going to check if the wavelength is still within the visible light. So for n equals to 3, so we shall have 3 times the wavelength which we want. D has not changed, so D is 1.7 times 10 power negative 6. Then sine, the angle has still remained 49. I just want to check if the value of lambda I obtain here is still in the visible range. Remember, the visible range is between 400 nanometers to 700 nanometers, or 4 times 10 power negative 7 meters up to 7 times 10 power negative 7 meters. That is the range of visible light. So I have 1.7 exponent negative 6 sine of 49 divided by 3. This is giving me a value which is, it is giving me a value of lambda which is 4.28 times 10 power negative 7. And this is the same as 4.423 nanometers. I think 423 is between that range. So that is enough wavelength. So this is going to be 4.28 times 10 power negative 7 in meters. You can check n equals to 1, and I know n equals to 1 will be already outside or below the visible spectrum, or to be above the visible spectrum. You can also check n equals to 4. We can check n equals to 4. For n equals to 4, I'll just say 1.7 exponent negative 6 times sine of 49. Remember, we're checking n equals to 4, so I divide by 4. When I divide by 4, I get 3.2 times 10 power negative 7, which is already below the visible spectrum. Therefore, the answer is going to be that one. Determine the wavelength, define the wavelength. Define wavelength. What is wavelength? You'll find such a question many times in waves. Define the wavelength of a progressive wave. Remember, progressive wave is a wave which transfers energy from one point to another point. That is a progressive wave. So what do we mean by wavelength? Of course, wavelength is the distance between two adjacent wavefronts, two adjacent crests, the minimum distance between two wavefronts, that is a wavelength. So I will simply define a wavelength as the distance between two adjacent. The word adjacent means one to the next without skipping any. So this is the distance between two adjacent wavefronts. Note that a wavefront is like a section through an advancing wave where all particles are in phase. A section in an advancing wave where all particles are said to be in phase is a wavefront. For example, if I sketch for you here something like this, and I'll make this to be in 2 dimensions. So this is like a wave, a water wave. When viewed from this side, you will see something like that. But when viewed from above, you may see horizontal lines like this. So all particles along this line here are in phase with each other. All particles along this line here are in phase with each other. All particles along this line are in phase with each other. So a section or a line through these particles that are in phase is called a wavefront. So the distance between two adjacent wavefronts is what we are calling the wavelength. So distance between this wavefront and that wavefront is what we are calling the wavelength. Or you can call it the distance moved by a wavefront during one cycle. Or I can say distance moved by a wavefront distance moved by a wavefront during one cycle or during one period during one cycle, during one period, during one oscillation, and so on and so forth. So that is a wavelength. Or the distance between the minimum distance between two adjacent wavefronts, the minimum distance between two wavefronts. Minimum is equivalent to saying adjacent, because minimum is the shortest between two wavefronts. Or I can say the minimum distance between two wavefronts. State what is meant by an antnode of a stationary wave. Of course, we know an antnode. That is like an antnode is not a particle, it is just a position where a particle vibrates with the maximum amplitude. So an antnode is going to be a position or a point where particles vibrate with the maximum amplitude. So this is the position where particles vibrate with the maximum amplitude. Position where particles vibrate with the maximum amplitude. A point where particles vibrate with the maximum amplitude. That is the antnode. And of course, the node is a point where particles are permanently at rest. Zero amplitude. You can't say vibrate with the zero amplitude, because if the amplitude is zero, then the particle is not vibrating. So for a node, particles are permanently at rest. For the antinode, particles vibrate with maximum amplitude. It is a position. It is not a particle. It is a position where particles vibrate with the maximum amplitude. That not maximum displacement, because amplitude is maximum displacement. But for a stationary wave, the amplitude varies. In other words, every particle could be having its own maximum displacement, so the amplitude varies. So we say maximum amplitude, not maximum displacement. I hope I've made myself clear. Okay. A loudspeaker producing sound of constant frequencies placed near the open end of a pipe, as shown in the figure here. So this is an open pipe. It is called a closed pipe because one end is now fixed. It is actually closed by a piston. So don't forget the fundamental mode, where for a closed pipe, the fundamental mode is going to be like this, which is a quarter a cycle. And you notice that for a quarter a cycle, before even seeing the questions, you know that the length x is going to represent a quarter of wavelength. Therefore, the wavelength is going to be 4 times x. Let's see the questions. A movable piston is at a distance x from the open end of the pipe. Distance x is increased from x equals to 0 by moving the piston to the left with a constant speed. So the speed of the piston is 0.75 centimeters per second. It is constant. The speed of the sound in the pipe is 340 meters per second. A much louder sound is first heard. A much louder sound is first heard when x is 4.5 centimeters. That is the first harmonic. We can call it the first harmonic. The first position of resonancy, or you can call it the fundamental mode of vibration if you want. Assume that there is an antinote of a stationary wave at the open end of the pipe. Determine the frequency of the sound in the pipe. So we have seen what happens. We have seen what actually happens. Okay, so let's determine the frequency of the sound in the pipe. We have already seen that x is going to be a quarter a cycle. If x is a quarter cycle, we can find the wavelength. So x, I'll start from here. We have already seen that x, which is the length, is a quarter of a cycle. At the point when we hear the first much loud sound, that is when resonance has occurred, the first harmonic has been established. So this one is going to mean that the wavelength is going to be 4 times x, which x is 4 centimeters. And I think this will be 4.5 times 10 power negative 2. That is the wavelength in meters. Okay, we want frequency. Remember, V equals to lambda times F. So the frequency F is going to be V, which is the speed of light. The speed of the sound. 340 divided by the wavelength, which is 4 times 4.5 times 10 power negative 2. I'll check my calculator. 340 divided by, open brackets, 4 times 4.5 exponent negative 2. So this gives me a frequency of 188.8. There are so many 8s. So to two significant figures, this is approximately 1900. So I'll write here a frequency of 1900 hertz. You notice that this looks so nice. However, avoid writing any answer which is not exact to less than two significant figures unless it is uncertainties, unless it is errors. Any answer which is not exact should never be written to less than two significant figures. I couldn't write so many 8s here because there were so many, but I could write it to two significant figures, which becomes 1900 hertz. Part 2. After a time interval, a second much louder sound, so that is the second time resonance occurs. That is going to be actually the second harmonic. Calculate the time interval between the first much louder sound and the second louder sound being heard. In other words, we want the time interval between the first harmonic and the second harmonic. The first harmonic and the second harmonic. Maybe just to remind you by sketching, I can remind you here by just sketching. If this was our pipe, let's say the piston is somewhere there, the other end is closed. The second much louder sound is going to form such a wave. And you notice that this will be now our distance x. This will be our distance x, but you notice that this is a half a cycle plus a quarter, a half a cycle plus a quarter a cycle. So this means x is equal to 3 over 4 lambda, which means that x here, because we already know the wavelength is 4 times 4.5 times 10 power negative 2. By the way, this is let me say 4 times 4.5. So this is 1.8 times 10 power times 10 power 1 or 0.18. Let me just write 0.18 here. That was the wavelength. So this is going to be 3 over 4 times 0.18. So that is times 3 divided by 4. So x, I'm calling this one x2. x2 is going to be 0.135 meters. Remember, x1 was 0.45. So we want the time interval between x2 and x1. So for x equals to 4.5 centimeters, this is x1. T1 is going to be 4.5. Remember, times 10 power negative 2, that is distance, divided by the speed. Because the speed is constant, the speed was given in centimeters per second. So I don't need to have this in meters. Let me have this in centimeters so that calculation is easy. So this is 4.5 divided by 0.75. This is in centimeters, this is in centimeters per second. And what is T1? And T1 is 6 seconds. T1 is 6 seconds when we have the first loudest sound. Then for X equals to, now this is 0.135 times 100. For X equals to 13.5 centimeters. What is T? Now this is going to be X2. So T2 is going to be equal to 13.5. I just changed this to meters. So it's 13.5 centimeters divided by 0.75 centimeters per second, because the speed is constant. So what is T2? And I'm getting T2 as 18 seconds. So the difference, the time interval is going to be the time interval. I will just call it interval. Is the difference between those two values of time. So the interval is going to be equal to 18 minus 6, which is going to be equal to 12. So the time interval is 12 seconds. There's another method that you could use. If you notice, initially we had something like this. For the first harmonic, we had something like that. Then for the second harmonic, we have a half plus a quarter. So the distance between the first and the second is simply going to be a half a cycle. Here we had a quarter, x1 was a quarter, a cycle. So here x is equal to a quarter wavelength, and here x is equal to 3 over 4 wavelength. So the distance moved. This is another method relying on that. So the distance is going to be equal to 3 over 4 wavelength minus 1 over 4 wavelength, which is equal to 2 over 4 wavelength, or which is wavelength over 2. The distance is wavelength over 2. And remember, the wavelength is 0.18. So this is 0.18 divided by 2, which is 0.09 meters. That is the distance between the first and the second. So it means now the time is easy. Because we have the distance between, then the time is easy. So it will be 0.09, that is distance over speed. The speed is given in centimeters, so I can change this in centimeters so that calculation is easy. I'll just multiply 0.09 by 100, so it becomes 9 centimeters divided by 0.75 centimeters per second. And this still gives you 12 seconds. So this is method 2. where you look at the first harmonic, x is a quarter wavelength. The second harmonic, x is 3/4 wavelength. So what is the difference? I subtracted together difference as lambda over 2. So that is the time we get here is the time between the time interval between the two harmonics. Okay, I hope that is fine. State the relationship between the intensity and amplitude of a wave. Of course, we already know from our AS intensity is directly proportional to amplitude squared. Intensity directly proportional to amplitude squared, or I is directly proportional to S squared. That is the relationship. Intensity is directly proportional to amplitude squared. That is the relationship. Microwaves of the same amplitude and wavelength are emitted in phase from two sources, P and Q. The sources are arranged as shown in the figure below. A microwave detector is moved along the path that is parallel to the line joining P and Q. A series of intensity maxima and intensity minima are detected. Remember, a maxima is for constructive interference and a minima is for destructive interference. When the detector is at point X, the distance Px is 1.84 meters and the distance Qx is 2.02 meters. The microwaves have a wavelength of 6.0 centimeters. Capture the frequency of microwaves. Remember, microwaves are electromagnetic and all electromagnetic waves travel at the speed of 3.3 times 10 power 8 meters per second. So you don't need to look for the speed. So we want to find the frequency. Frequency from the general wave equation is V over lambda, which is going to be 3 times 10 power 8 meters per second over the wavelength, which is 6 centimeters, 6 times 10 power negative 2. To change it to meters. For my calculator, 5 divided by 3 divided by 6. So this is giving me 5.0 times 10 power 9 hertz. So that is the frequency. Describe and explain the intensity of the microwaves detected at X. So we want to find out whether it is an intensity maximum or an intensity minimum. But how do we do this? We must find the path difference or the phase difference. Let's come back to the diagram and find the path difference. First of all, remember the wavelength is 6 centimeters. The wavelength is 6 centimeters. What is the path difference? Oh, the paths are in meters, but I will just multiply by 100. So the path difference, I'll use this symbol sigma for path difference. We subtract. So the path difference is 2.020 minus 1.840. Let me subtract. Find the path difference. 2.02 1.84. This is 0.18. Remember, this is in meters. If I want it in centimeters, so it means the path difference is going to be multiply that by 100. This will be 18 centimeters. This is an equation. This is an equation. I'm going to divide the two equations. Path difference divided by wavelength. This is going to be 18 divided by 6, which is equal to 3. Do you notice that the path difference is 3 times of the wavelength? And remember, for constructive interference, the path difference must be a whole number times wavelength for constructive interference. Yet for destructive interference, the path difference was equal to n plus a half, I think, times lambda. This is for destructive interference. This is for constructive interference. So since we are seeing that it is a whole number times lambda, the path difference is a whole number times lambda, then there must be constructive interference at x. Constructive interference means an intensity maxima. You could also find the phase difference by, of course, phase difference, lambda corresponds to 180. Lambda wavelength, lambda corresponds to 360 because that's one complete cycle. So just say 360 times 3. That is 1080. So the phase difference, theta of phi is 1080 degrees because lambda corresponds to one cycle, which is 360 degrees. So 3 times, these are 3 cycles. Okay, so describe and explain the intensity of the microwaves detected at x. So we can simply say at x, path difference equals 3 lambda, or you can say phase difference equals to 1080 or 1080 degrees or 0 degrees by the way, because 1080 degrees and 0 degrees all mean constructive interference. So at x, path difference is 3 lambda, or phase difference is 1080 degrees or 0 degrees. What does that mean? Constructive interference occurs at x. Constructive interference occurs at x. So an intensity maximum is detected at x. As simple as that. At x, the path difference is 3 lambda. Constructive interference occurs at x, so an intensity maximum is detected at x. Note that, how do we know that it is constructive? We know the conditions of constructive. As long as the path difference is n times lambda, that is a whole number times lambda, that is going to be constructive interference. If it is n plus a half lambda, that is an odd number divided by 2. It can be 3 over 2 lambda, anything divided by 2, that is going to be destructive interference. So that is, for this particular question, it is constructive. Describe the effect on the interference pattern along the path of the detector due to each of the following separate, not at the same time. Following separate changes. Number 1, the wavelength of the microwaves decreases. The wavelength of the microwaves decreases. What happens to the interference pattern? What is the effect of the wavelength? Since we have only 2 sources, we can think about this in the same way we would think about a double slit. And remember, for a double slit, lambda is equal to ax over d, where a is the separation of the slits, x is the fringe separation, d is the distance between the slits and the screen, or which in this case will be the detector. So the wavelength is decreased. When lambda decreases, A is not changing, D is not changing, so X is going to change. You see that lambda is directly proportional to X. So when lambda decreases, X also decreases. Remember, X, not the point X, but X is the distance between the fringes, the distance between two successive maxima or two successive minima. So when lambda decreases, then the distance between adjacent intensity maxima, remember when I say adjacent, that is one to the next. Distance between adjacent intensity maxima or the distance between adjacent intensity minima. Minima is plural, maxima is plural, meaning two. The distance between adjacent intensity maxima, or let me add here two. The distance between two adjacent intensity maxima or two adjacent intensity minima decreases. That is X. In other words, the fringe separation decreases. The fringe separation X decreases. That's what it means. When the distance between adjacent intensity maxima or the adjacent intensity minima decreases because lambda is directly proportional to X. Number two, the phase difference between the microwaves emitted from the source changes to 180 degrees. Let's see the initial phase difference. If it was 0 and then it is changed to 180 degrees, then it means they just swap places. The maxima and minima swap places. So here they said microwaves of the same amplitude and wavelength are emitted in phase. That means initially they were the microwaves were emitted in phase. The phase difference between the sources was 0. Now the phase difference between the sources is 180. It means the waves emitted from one source are 180 degrees out of phase or ahead of the waves emitted up from the other source. What does that imply? Very fast somebody will say destructive interference occurs at point X. That is very true. We would expect that now at point X where we had a maxima, we shall have a minima. What will have happened? They have swapped places. At X where there was a maximum, if the one source is 180 degrees ahead of the other, then we expect at X to be a minimum. So that means the maxima which was at X is going to take up the place of another minima which was at another neighboring point. So what has happened? The intensity maxima and intensity minima exchange places. Intensity maxima the intensity maxima and minima exchange places. Exchange or swap places. The intensity maxima and intensity minima exchange places when the phase difference between the sources is 180 degrees. So they just simply exchange places. For a progressive wave, state what is meant by the period. What is meant by the period? Of course, this is an easy question. Period is the time for one complete cycle, one complete vibration, one complete oscillation. That is period. Time for one oscillation, time for one oscillation time for one cycle, time for one vibration, that is period. You don't say all these, you just choose one, time for one complete cycle. Somebody can define the period in more details and say that this is the time between adjacent wavefronts. Time between two adjacent wavefronts. That is the period, or it is the time between points, two adjacent points that are in phase. It can be the shortest time between two wavefronts. Shortest time between two wavefronts, or shortest time between points that are in phase. That is the period. Then the wavelength, we have already defined the wavelength as the distance between two adjacent wavefronts. Distance between two adjacent wavefronts, that is wavelength. Distance between two adjacent points that are in phase. Distance between two adjacent points on a wave that are in phase. We say this is the distance moved by wavefront during one cycle. So that is the wavelength. Figure 4.1 shows the variation with the time t of the displacement x of two progressive waves p and q passing the same point. So here we have the figure. So remember, these are progressive waves. A progressive wave is one which transfers energy from one point to another point. So we have wave P and wave Q. The speed of the waves is 20 centimeters per second. Capture the wavelength of the waves. Of course, from the graph is of x, that is displacement, against time. So they have the same, I think they have the same frequency, they have the same period. So from the graph, when I consider wave P, the period is 0.6, so I can find the wavelength. So using the general wave equation, V is equal to lambda times F, it implies that the wavelength lambda is going to be V. V is 20 centimeters 20 centimeters per second. So I will say V is 20 centimeters per second divided by, why don't I use T directly? Because this means that V is equal to lambda. F is 1 over T, so this is going to be lambda over T. That means lambda is going to be V times T. So this will be times T, which T is 0.60 seconds. And this is giving me 20 times 0.6, that is 12 centimeters. They want the answer in centimeters, so this is going to be 12. Remember here how I came up with V over as lambda over T, F is equal to 1 over T. So I just substituted for F. So lambda is going to be 12 centimeters. Okay, determine the phase difference between the two waves. We just need the time out of step. The word phase difference can only be applied to waves which have the same period of frequency. If they don't have the same period of frequency, then we cannot apply the word phase. So let's find the time out of step. Let's say from here up to here, these are two waves, but at this point, particles are passing equilibrium for both waves. So this is at time equals to 0.2. The scale on the x-axis is 0.2 divided by 10, which is 0.02. So we have 1, 2, 3, 4, 5. So this should be 0.3. And here, 1, 2, 3, 4, 5, this should be 0.05. 0.50. 0.50. So we want the time out of step. I find the time out of step, I'll call it small t. Time out of step is 0.5 minus 0.3, which is 0.2 seconds. That is the time out of step. So phase difference, they want the answer in degrees. Phase difference is going to be 360 degrees into time out of step over the period, which is going to be 360 into time out of step, which is 0.2, as compared to the period, which is 0.6. So I'll check my calculator. 0.2 divided by 0.6 times 360. That is 120 degrees. So the phase difference is 120 degrees. Of course, another angle which is acceptable will be 240 degrees. 240 degrees would be acceptable. But this is the most direct answer that you can see from the graph. That is the most direct answer. Calculate the ratio intensity of wave Q over intensity of wave P. We know that we have already seen that intensity is directly proportional to amplitude squared. So we want intensity of Q divided by intensity of P. This is going to be equal to a constant amplitude of Q squared over a constant amplitude of P squared. So this is going to, the constant of course will cancel out. Amplitude of Q squared, amplitude of Q from the graph, you see that the amplitude of Q is this one, which is 2.0 millimeters. So that is 2.0 squared divided by, I don't need convert because the unit, it is a ratio, the units cancel out. The amplitude of wave P is, I think, 3. So this will be divided by 3 divided by 3.0 squared. So I just press my calculator. 2.0 squared divide by 3 squared, that is 0.44444. So I'll just write two significant figures, 0.44 as the ratio. The two waves superpose as they pass the same point. Use the figure to determine the resultant displacement at t equals to 0.45 seconds. Let's look for 0.45 seconds. Remember the scale is 0.02 on the x-axis. So this is 0.42, 0.44. 45 must be in the center here, where on this wave it is here, the amplitude is that, and on the other wave the amplitude is here. So this is 1.0, I guess, for wave Q, and this is negative 3.0. Of course, this means in the opposite direction. So we want the total displacement according to the principle of superposition. It is going to be the sum, the algebraic sum of those amplitudes. So we have 1.0 for Q plus negative 3.0 for P, and the total here is negative 2.0. Therefore, the amplitude here is going to be, let me add zeros because anyway, that is fine. The amplitude here is going to be negative 2.00 millimeters or negative 2.0. The principle of superposition says the resultant is the algebraic sum. So we have seen at 0.45 seconds, the amplitude of wave Q is 1 from the graph, and at the same time the amplitude of wave P is negative 3 from the graph. So we add algebraically and we get negative 2.0. Okay, when monochromatic light, remember mono means one, light of the same color, same wavelength, same frequency. When monochromatic light is incident normally on a diffraction grating, the emergent light waves have been diffracted and are coherent. Explain what is meant by diffracted waves. What are diffracted waves? We know the meaning of the word diffraction, spreading of a wave. As it passes through a narrow slit, the wave is spreading into regions of geometrical shadow. So what we mean by diffraction, if this is a narrow slit, when waves pass through the slit, they spread into regions of geometric shadow. That is what we call diffraction. So when we talk about diffracted waves, we mean that waves spread at each slit or gap into regions of geometric shadow. Waves that have spread into regions of geometric shadow as they pass through a narrow slit. So here we are saying waves spread. The word spread is very important. At each slit or call it gap, because we are talking about a diffraction grating which is made up of numerous slits or gaps. So the waves spread at each slit or gap into regions of geometrical shadow. What do we mean by regions of geometrical shadow? You see this area here and the area above here. If the waves were to travel in a straight line, they wouldn't reach in that area. So that area would be a shadow. This area will also be a shadow, but the waves spread into those areas. So we say they spread into regions of geometrical shadow. Coherent waves. We know what we mean by coherent waves. The word coherency means maintaining a constant phase difference between two waves. So coherent waves, these ones are waves which maintain a constant phase difference between them. Waves maintaining a constant phase difference between them. Those are coherent waves, waves maintaining a constant phase difference between them. Light consisting of only two wavelengths, lambda 1 and lambda 2, is incident normally on a diffraction grating. The third order diffraction maximum of the light of wavelength lambda 1, this is third order, n equals to 3, and the fourth order, n equals to 4. Diffraction maximum of the light of wavelength lambda 2 are at the same angle theta, so theta is the same for both. The direction of the incident light. Show that lambda 2 over lambda 1 is 0.75. Explain your working. I know some of you would love to forge. So there is no forging here when they say explain your working. They expect that you must be obtaining this from first principle. So from the expression for diffraction grating, we know that n lambda is equal to d sine theta. Remember, sine theta is the same. So sine theta will be the same. They are incident normally on the same diffraction grating, meaning that d is also the same. However, for the first one, we have n is 3, so 3 times the wavelength is lambda 1 is equal to d sine theta, and also 4 for n equals to 4 times lambda 2 is equal to d sine theta. So we combine the two equations by dividing. Since I want lambda 2 over lambda 1, so I'll say 4 lambda 2 divided by 3 lambda 1 is equal to d sine theta over d sine theta, and this is equal to 1. So it means 4 lambda 2 over 3 lambda 1 is equal to 1. So I want lambda 2 over lambda 1, so I just get the ratio. Lambda 2 over lambda 1, 3 goes up and 4 comes down. And this is the same as 0.75. The difference between the two waves is two wavelengths is 170 nanometers. Difference meaning subtraction. Difference is meaning subtraction. Determine wavelength lambda 1. So assuming lambda, from this expression here, you see that lambda 2 over lambda 1 is less than 1, meaning lambda 2 is larger. Meaning lambda 2 is going to be larger. So we shall say that lambda 1 minus from this expression here, okay, let me just do simple mathematics. From this expression here, we have that lambda 2 is equal to 0.75 times lambda 1. That is lambda 2 is 0.75 times lambda 1 from this expression in part 1. And they have told us that the difference is 170 nanometers. In other words, lambda 1 minus lambda 2 is 170 nanometers. But lambda 2 is 0.75 lambda 1. So we shall say lambda 1 minus 0.75 lambda 1 should be equal to 170. I find lambda 1. So this is there is a 1 in front of lambda 1. Lambda 1 minus 0.75 lambda 1 gives us 0.25 lambda 1. There is a 1 in front here. So we subtract 1 minus 0.75. So this is equal to 170. So So I just divide 170 divide by 0.25. That is 680. So it means lambda 1 is 170 divided by 0.25, which is 680 nanometers. So that is yes. Yes. Just let me know immediately because I am still recording. Yes. Mm. How much? How much is that? Okay, just give me like as soon as I finish recording, I will upload it on for you. Okay. 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 Sorry for the break. For the break, I have some flu. By reference to two waves, state the principle of superposition. We have indirectly stated the principle of superposition, and I think by now you should be having an idea about it. In the previous question, where we added the displacements, we added the amplitudes, actually, we added displacements. So the principle of superposition tells us that when two waves interfere or overlap, and we want to find the resultant displacement, we just sum up the individual displacements. So we shall simply say that when two waves when two waves meet at a point, the resultant displacement is the algebraic sum of the individual displacements of each wave. We just simply sum up the displacements of each wave to find the resultant displacement according to the principle of superposition. So when two waves meet, they must be meeting or overlapping. When two waves meet at a point, the resultant displacement at that point is the algebraic sum of the individual displacement of each wave. The sum of the displacements of each wave is what we call the principle of superposition. What is meant by coherency? Now the word coherence will be common to us. The word coherence means maintaining a constant phase difference between waves. So maintaining a constant phase difference between the waves. maintaining a constant phase difference between the waves. When two waves maintain a constant phase difference, we say that the sources are coherent. Two coherent waves, P and Q, meet at a point in phase and superpose. They meet in phase. In other words, the phase difference is 0. Wave P has an amplitude of 1.5 centimeters. Intensity is I. The resultant intensity, remember intensity is a scalar quantity, so we define the resultant by adding. The resultant intensity at the point where the waves meet is 3I. The resultant intensity is 3I. Calculate the amplitude of wave Q. Number 1, we know that intensity is directly proportional to amplitude squared. That's number 1. And to find the resultant intensity, we must find the resultant amplitude, which is the algebraic sum. So the resultant intensity, I will quote IR, is equal to the constant into the resultant amplitude. Let's say the amplitude of P is A. Wave P has amplitude of 1.5 and intensity that. Let's say the amplitude of Q is A and the amplitude of P is 1.5. So this will be plus 1.5. We have added the amplitudes, but remember this is squared. That is for the resultant. But again, for P alone, its intensity IP is equal to the constant K into the amplitude of P, which is 1.5, and this is also squared. So we are going to just combine these two equations and I'm going to divide. So IR divided by IP should be equal to the constant has cancelled out. So this is going to be A plus 1.5 squared divided by 1.5 squared. Remember IR is 3I. So 3I divided by IP, which is I, is equal to A plus 1.5 over 1.5 squared. This is also squared. So I has cancelled out. I just do long algebra for those of you not doing mathematics. But a mathematician, this is very short. So I have 3 equals to that. I'll first cross multiply. So we have 3. I will stop here. The algebra stops here. I will just put in the calculator 3 times 1.5 squared. Then square root. Then minus 1.5. And I'm getting this as, okay, for the mathematicians, they will say, now how do you get that? So I'm getting 3 times 1.5 squared equaling to A plus 1.5 squared. I find the square root both sides. That's what I've done. When I remove the square root, this one cancels with the square root. I get 3 times 1.5 squared. Then I find its square root. So I remain with A. I just subtract 1.5 from the value on the left. And I get my value of A as 1.098, which is approximately 1.1. So the amplitude is 1.1 centimeters. I didn't change the units of amplitude because I knew the answer would remain in the same unit of centimeters. Okay. The apparatus shown in the figure 5.1 is used to produce an interference pattern on a screen. So you see these are two slits. That is a double slit. That's Young's double slit. They have given us A, D. The wavelength is 680 nanometers. Light of wavelength 680 nanometers is incident on a double slit. Remember, for a double slit, lambda is equal to AX over D. The slit separation is A. The separation between adjacent fringes is X. Fringes are viewed on the screen at a distance d from the double slit. Distance d is varied from 2 meters to 3.5. The variation with the d of x is shown in the figure. Use the figure 5.2 to determine the slit separation A. So remember, lambda is equal to ax over d. We have a graph of x against d, so I make x the subject. So x is going to be lambda times d divided by a. So this will be the gradient if you compare with the y equals to mx plus c. On the y-axis, we have plotted the fringe separation. On the x-axis, we have plotted d. So the gradient is lambda over a. There is no intercept. Okay. So the gradient is equal to wavelength over, in other words, the gradient is directly proportional to the wavelength and inversely proportional to the slit separation. Let's find a gradient, or even if we don't find a gradient, we can just take a pair of values from the graph. So A is equal to lambda times d over x. So lambda is 680 nanometers, so times 10 power negative 9. D distance d is varied from 2 meters to 3.5. So let me take 2 meters. So I'll take d as 2.0 meters because I want to consider the corresponding value of x as 4. That is 4.0 times 10 power negative 3. Or you would get 680 times 10 power negative 9 times d, which is 3.5, divided by the corresponding value of x, which is in the center here. Because the scale on the vertical is 2 divided by 5, 2 divided by 5 is 0.4, 6.4, 6.8, that is 7. So this will be 7.0 times 10 power negative 3. I will simply press my calculator to find A. You could choose different corresponding values of x and d, no problem. So I have 680 exponent negative 9 times 2 divided by 4 exponent negative 3. So I'm getting exactly 3.4 times 10 power negative 4. 680 exponent negative 9 times 2, 4 exponent negative 3. Yes, 3.4 times 10 power negative 3. It's always good to check your answer. The laser is now replaced by another laser that emits light of a shorter wavelength. Shorter wavelength, that is a smaller wavelength. Remember, we have already seen that wavelength is directly proportional to gradient. So since the gradient is equal to lambda over A, in other words, if the wavelength is smaller, the gradient should be shorter. The line should be less steeper. And remember, gradient is change in x over change in d. So what does that imply? The change in x is going to be very small, yet the change in d is going to be very large. That is what it means. That is what it means. For the line to be very steep, the change in x is small and the change in d is very large. So I'll draw a less steeper line. Since they didn't give us any values to use, so I'll just look for a less steeper line where the change in the x values is very small, is smaller than the one which we had before. Increase the weight. Okay, so such a line is better. You can see the change in x values. In the x values is between 0.123, 0. Because it is 0.4 times 3, 1.2 minus 0. Yet here it was 7 minus 3, that was 3. So this change in x is small, but the change in y is large. So the graph would be like that. In other words, it diverges here. You see, it is diverging. They are moving apart to show that the line is less steeper. It can't be parallel because if it is parallel, it means they have the same gradient, so the wavelength has not changed. So the graph must be less steeper. It is a straight line, so you should try to draw a straight line. I hope I tried a straight line. Maybe I need to draw a better one. It doesn't look a straight line to some people. Okay, so that is my graph. You can draw a better straight line than mine. It should be less steeper. State the conditions required for the formation of a stationary wave. Conditions for the formation of a stationary wave. We can't have a stationary wave if the two waves do not overlap. So the waves must overlap. That's number one. These waves should have the same frequency or wavelength. They should be traveling at the same speed, but instead in opposite directions. For a stationary wave to be formed, the waves should be of the same type or the same kind. You can't form a stationary wave between a light wave and a water wave. Not at all. Therefore, the two waves of the same type two waves of the same type two waves of the same type, same frequency or wavelength, same frequency or wavelength, traveling at the same speed. Traveling at the same speed in opposite directions. So we have two waves of the same type, same frequency, wavelength, traveling at the same speed, same type, same frequency. It is important to notice that they are in opposite directions. They must overlap. So they overlap to form a stationary wave. So two waves of the same type, same frequency or wavelength, traveling at the same speed in opposite directions overlap. They must be overlapping. They must be meeting at a point to form a stationary wave. Okay. The sound from a loudspeaker is detected by a microphone that is connected to a cathode ray oscilloscope. Figure 4.1 shows the trace on the screen of the CRO. So this is the figure showing the trace on the screen of the CRO. In air, the sound wave has speed of 330 meters per second and a wavelength of 0.18 meters. Calculate the frequency of the sound wave. Calculate the frequency of the sound wave. So let's find the frequency. Of course, we know from the general wave equation, V equals to lambda F. Frequency is going to be equal to lambda, which is, speed, which is 330, divided by the wavelength, which is 0.18. And this gives us so this gives us to two significant figures. This is 1,800. You can also verify to two significant figures, 330, which is 1,800 hertz to two significant figures. I just chose a more convenient value. Determine the time-based setting in seconds per centimeter. I will upload a video of how to manipulate cathode ray oscilloscope readings for most of you who lack experience. I'll upload a video for how to deal with those so that people can practice questions about time-based settings, amplitude, and so on and so forth. I'll upload a video at the end of waves. So time-based setting, we want to determine the time-based setting in seconds. So normally my students prefer to use a simple expression that the period t is represented by the length correspond to one cycle times x, which is the time-based setting. That's what normally my students prefer to use. T is period, L is the length representing one complete cycle, and x is the time-based setting. Remember, on the x-axis, on the time-based setting is going to help us to find the period. The time-based setting times the length, which is representing one cycle on the trace shown here, is going to be the period. So we need to find x, remember, which is the time-based setting. But the period is 1 over the frequency. Remember, period is 1 over f. So I'll just get this expression. So the reciprocal is 0.18 over 330. Instead of using this, I just chose this because I want to get a more exact value. I will round off in the final answer rather than rounding off at this stage. So I just get the reciprocal of this, that is the period. From the graph, let's see what length represents one complete cycle. So we can say, okay, I will draw a horizontal line through the trace so that it is easy for me to see one complete cycle. And you notice that if I start from here, one complete cycle is almost in the center here. And every 5 small squares represents 1 centimeter. So one small square is 1 over 5 in centimeters, one small square. But how many small squares do I have for one cycle? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26 and a half. So I have 26.5 small squares, but each small square is 1 over 5 centimeters. So this is the length representing one cycle. And 26.5 divided by 5, this means the length representing one cycle is 5.3 in centimeters. So L is 5.3 in centimeters. So this is 5.3 centimeters times x. Remember, this is period, and period is in seconds. So this is in seconds. So I'm now just going to divide to find x. I'm just going to divide, find x. So x is going to be 0.18 divided by 330, again divide by 5.3. This is in centimeters, this is in seconds. So 0.18 divided by 330 divided by 5.3. This is giving me x as 1.029 times 10 power negative 4. Remember, the numerator was in seconds, the denominator was in centimeters, so it becomes seconds per centimeter. Therefore, the answer here is approximately 1.0 times 10 power negative 4. I do long algebra just for the non-mathematicians. So for the mathematicians, you can always have a shortcut. The intensity of the sound from the, by the way, for this, I'll record an independent video for this particular area so that people learn the practice of that. The intensity of the sound from the loudspeaker is now halved. Intensity is halved. Remember, intensity is directly proportional to amplitude squared. The wavelength is unchanged. Assume that the amplitude of the trace is proportional to the amplitude. The amplitude of the trace is proportional to the amplitude of the sound wave. Sketch the new trace shown on the screen of the CRO. So we need to find the amplitude, the new amplitude. Remember, intensity is equal to K amplitude squared. Intensity is K amplitude squared. So this is going, let's say this was the first intensity. The second intensity, I'll call it I2 or I1 is going to be, because the intensity is halved, I1 is a half of I. It is halved. I1 is a half of I, and of course this is going to be a constant K times A1 squared. So I have two equations to divide. The second and the first, so I will divide the second equation by the first equation. This divide by that. So I have that a half I divided by I is equal to K amplitude A1 squared divided by K, the first amplitude squared. So I has cancelled and K has cancelled. So as a mathematician, you notice that A1 squared is equal to a half times A squared, which means A1, when I get the square root, A1 is going to be A divided by the square root of 2. The amplitude that we had originally, we can find it from the graph. The amplitude we had is this one. Remember, on the vertical, 1 centimeter is 5 boxes. That means one box is 1 over 5 centimeters. So how many boxes represent the amplitude? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is times 12. 1 over 5 times 12, which is 2.4 in centimeters. So the amplitude, the original amplitude was 2.4 centimeters. So I'm getting the new amplitude here. So 2.4 centimeters divided by root of 2. 2.4 divided by root of 2. And this is 1.7 centimeters. 1.7 centimeters is our new amplitude. But how many small squares will those ones be? Remember, one small square was representing 1.5 centimeters. How many small squares do we need to represent? One small square was representing 1 over 5 centimeters. How many small squares do we need to represent 1.7 centimeters? So the number of small squares we need are called n times what one small square represents should give us 1.5 centimeters. Number of small squares times 1 over 5. One small square is 1 over 5 centimeters. So I'll just say 1.7 times 5. That is 8.5. So the number of small squares which we shall consider is 8.5 for the new amplitude. So the new amplitude will be represented by 8.5 small squares. That is to be exact. So I'll just count 1, 2, 3, 4, 5, 6, 7, 8.5. Downwards 1, 2, 3, 4, 5, 6, 7, 8.5. 1, 2, 3, 4, 5, 6, 7, 8.5. Remember the other things remain the same, the wavelength remain the same. So I'll draw a graph which is inside the first graph. So that is our new graph. That is our new graph. I try to be extremely exact. That's why I had to do a lot of calculations. It's not about guessing. You must know the basics. Okay. The loudspeaker in B is held above a vertical tube of liquid as shown. Okay. A tap at the bottom of the tube is opened so that liquid drains out at a constant rate. Liquid drains out at a constant rate. The wavelength of the sound from the loudspeaker is 0.18. The sound that is heard first becomes much louder. That is the first resonance. The first resonance or the first harmonic at level A. So we have the first resonance at level A, so I will have something like that for reference. The next time that the sound becomes much louder is when the liquid surface level reaches level B. So that is the second harmonic.